Okay, so thank you guys very much for dealing with me this week as I'm having to travel, and I'm going to be trying to continue on with our discussion of wastewater treatment and how to design. So we're going to continue on where we left off today, where the wastewater characteristics and the treatment goals that we were discussing. And one of the first things we want to think about is to understand the wastewater pollutants that are coming in and what those types are and the forms that they're coming in. And as we were talking about earlier, if you have ammonium, you're going to need oxygen, versus no ammonium, then you will need nitrate. I'm sorry, if you have ammonium, you're going to want oxygen. When you have nitrate, then you're going to not want oxygen. The other thing is that we want to know our average discharge concentrations that we're desiring, or the particular loads that we're trying to get to. This is going to be really important when it comes to thinking about is the area that we have available feasible for using our treatment wetland system. And again, we were talking about earlier the climate being important, particularly for the temperature and removal processes, because your microbes are not going to be working, particularly if it's really cold. And also, if it's really cold, you're not going to have plants to be able to do those removal processes either. When you're thinking about the discharge from your wetland, is it going to be discharging into another treatment? So you can actually have a wetland going to another wetland, such as a surface flow wetland going to a subsurface flow wetland. What are the permits that are going to be required? And we'll get into this more in a few weeks as to like determining which permits we need to go ahead and fill out before we get started. And then there's also the storage component, where you're thinking about, is the system recycling things like nitrogen being recycled through the plants as they die, and then it goes into the system and then can be taken back up again, or things like irrigation. Can you actually use the water to irrigate with, which we had talked about a few months ago about how the wetland itself is actually being irrigated. So these are also some other things we need to think about. So one of the important calculations we have to make before we can really get started is this term called hydraulic loading rate, which you may remember from back in hydrology. And this ultimately is referred to either as HLR or Q, little q, and it's measured in meters per day. And then it equals your inflow rate, so how much water is being flowed into your wetland divided by the wetted wetland area. Typically, we can convert these numbers by 100 if you're trying to get it to centimeters per day. And traditionally, you want this to be less than 10 centimeters per day. Usually between 2.5 and 5 centimeters of loading per day is usually considered to be the best loading rate for your systems. Because if you overload the system, it's not going to be doing anything, as we talked about earlier, and it can also kill your plants. There's also this term called the theoretical detention time, and so this is how long your theoretically your water is going to be detained in your wetland, and this is determined by the volume of your basin divided by the flow rate through the wetland, and this typically is actually an average of your inflow and your outflow rates. So Q in plus Q out divided by 2. And if you refer back again to the hydrology, you'll see a very similar calculation. There's also the detention time in wetlands, and this is a slide that literally was from earlier in the semester. So you have your mean hydraulic retention time, which is your HRT. So it's your volume over your Q, as we were just talking about. Then you have your actual detention time. It's a more conservative way of measuring, and if you were to want to refer to the treatment wetlands book, it's on page 23. And this is your active flowing water that's moving through your system, such as if you have a system that has a river that's moving through to the outlet, and then it's divided by your inflow rate. So not your average, but your just overall inflow rate. This also is equivalent to your porosity, so the fraction of your volume occupied by the water times your mean water depth, and then times your active area of your wetland divided by Q. The porosity is going to be important, particularly when you're thinking of a subsurface wetland where your water is moving underground. The last equation will be your nominal detention time. It's an even more conservative way. So if you're going to make sure that no matter what, your wetland is being estimated in the most conservative, going to work manner, you can use the nominal detention time. And this is where you've got your nominal volume, which is your length times your width times your height of your overall wetland divided by the inflow concentration. I'm sorry, not inflow concentration, your inflow load, so your meters cubed per day. So here's an example of a surface flow constructed wetland. It's designed specifically for pollutant removal, so we're not talking much about the ecological aspects of the system. You have over here where your concentration is in influent coming into your wetland. You will have this background concentration here. So no matter what, your wetland will always have a little bit of nitrogen, a little bit of till suspended solids, and other types of concentrations of contaminants. Then you have your weir and your outlet where your, it could also be a standpipe, and it's kept at a certain depth. If you want to change that depth, then you can have a standpipe where you can adjust it. And then it's also your flow control. And then you have your effluent concentration that's been leaving your wetland. So it comes in through the influent, moves to the wetland while it's treated, and then it has an exit where it has the concentration out. We can actually predict the removal rates in wetlands, but it's not an exact science, as we were talking earlier. There's going to be differences with your soil type, your plant type, the temperature. There's a lot of impacts that can influence what your outlet concentrations are, but we have a pretty good idea of what we can estimate. There's been a lot of research done on this, and here are some compiled graphs based on mass pollutant per area entering a wetland, and then the predicted percent removal. As I was talking earlier today, I'm not a huge fan of percent removal because it can be highly variable. I'm more of a person that's interested in the inflow concentrations, and so these are nitrate inflows from grams of nitrogen per meter square per year. So when you look at the percent removal, you have a better idea of the load that's going in, and of that load, how much of it was removed. So if you have 100 grams of nitrogen per meter square per year coming in, and over 50% of it is removed, you have a good idea that you have around 50 grams of nitrogen per meter square per year leaving. All right, so this is compiled from regional wetlands, and it's used to estimate performance expectations. So it has a 95% confidence interval, so you can tell, like, particularly if we look here at this median, we can go anywhere from, so this is around probably 60 grams of nitrogen per meter square per year. We can go anywhere from around 20% removal up to 78% removal. So there's a pretty wide change. And the same goes for this nitrate concentration down here. So these right here are looking at Ohio and wetlands versus, and then you can look at the Louisiana and then just other wetlands in general. And you'll see that there's some scattering of how these systems work based on even the location. All right. So how do we determine how well our wetlands going to work? Will it be 25, 50, 100 grams of nitrogen per meter square per year? Like, how do we know what our performance will be based on our loading? So we can use multiple regional studies with similar loads. And this is the ideal situation. As we talked about earlier today, this isn't always feasible because for instance, in Nebraska, we don't have a ton of treatment wetlands. And so if that is not going to be feasible for you, you can then use data from outside of your region. However, you want to be sure to avoid placing too much emphasis on the wetland performance that's really high or really low. So you kind of want to find like an average removal rate for a similar wetland. And an alternative could be using studies at wetlands that are similar size if possible. So if you have to go outside your region, you can also look at similar sized wetlands. Here's a table from your book on page 451. And ultimately, it's showing you the different size wetlands. These are all from Midwestern areas and the nitrate retention of grams of nitrogen per meter square per year and kind of what you can anticipate. So for instance, this created river diversion in Ohio was about a 3-hectare wetland that had around 32 grams of per meter square per year of nitrate retention, which was relatively similar to a 1-hectare ag wetland system. There's one in Illinois that had a very similar retention rate as well. Relative size, geographic location, small variation in retention rates would make these studies a good basis for like a Midwest design specifically. So this is a good idea for instance, if you're designing in Nebraska. A little higher than 10 to 20 grams of nitrogen per meter square per year is a rule of thumb described in text for low concentration non-point source pollution sources. So for instance, these are systems that are receiving ag water from runoff. This is not going to be similar to or exact science for wastewater treatment, for instance, from a municipality. But if your municipality is releasing water that's similar to ag water, which likely for your design will be true, you can anticipate likely a nitrate retention removal in this range. So the major method that we use to determine how much removal is going to be this KC star method. And ultimately we have this change of concentration as you flow through the wetland, and it equals this aerial removal rate, and these values are located on a PDF that I've uploaded to Canvas. And then you take your concentration and you subtract it from your background concentration. And so the Q is your hydraulic loading rate, talked about earlier. Your C is your chemical, and then the Y is the fractional distance from the inlet to the outlet, so the distance it takes for a water particle to move from the inlet of your wetland to the outlet of your wetland. So let's look at this again. We've got our C effluent, our CI, our influent concentration coming in. We've got the background concentration, our C star in the back here, and then we have our C out, just as a reminder of what these systems look like for a surface flow system. So one of the things we have to integrate into this is that we have an outflow concentration and an inflow concentration along with your background concentration. And so for the KC star, we'll then adjust this, the equation. And we're not going to go into all of the analytics of how we got to this equation. I think it's a little bit beyond this class, but ultimately end up with our C outflow concentration minus our background concentration divided by our inflow concentration minus our background concentration. And this is going to be equal to the exponential of your negative K value, which you'll get in your sheets that we'll discuss further next week, divided by your hydraulic loading rate. So it's critical that you have your hydraulic loading rate and you know your constraints of what is coming in and what your goal is for coming out of the system. Or if you're trying to determine what is coming out of the system, you can have such as your inflow concentration and then determine what your outflow would be. That's by rearranging the equation. So when you're sizing, the big question is, do you have enough space to meet your objectives or the goals of your overall project? And it's going to vary with the particular pollutants, and it will require for different treatments. So your design wetland for pollutants will require that you have a large enough area. And if you don't, then you're going to have to adjust either your goals or the amount of water your loading rate, or you'll have to increase your size of your wetland. So we can rearrange the equation we were just discussing to find the area that's required to meet our goal. So this would be a great exercise for you to do, for instance, for your design experiment, where you can determine for their goals what the size wetland you would actually need. And this would be your area equals your flow divided by your K, which is that removal rate constant we were talking about. You take the log, the natural log of your C, your concentration at your outlet minus your background divided by the concentration in the inlet minus your background concentration. This should only be considered as an estimate, and it's pretty simple, but it does have a few drawbacks that we'll discuss here later. So if we were having class, and I encourage you to do this with your, perhaps if you're with a group or if you're just thinking at home, take a few minutes to determine ideas to improve wetlands efficiency to remove. So we talked a little bit about nitrogen processes and the importance of nitrogen processes. And we'll come back here in a few minutes after you think about it.